This lecture is the start of chapter 13. This is an introduction on chapter 13. It's radiation exchange between surfaces. We're specifically talking about enclosures with non-participating media. I'm going to define what these are, and I'm going to give you an introduction on this chapter in the next few lectures. But in general, what we have learned in the past lecture, or in the past chapter, chapter 12, those are more concepts that we will now be using in order to actually analyze real radiation problems. Without that type of understanding, this would all look very mechanical. This would all look like you're just following some rules and you would not know why you're following those rules. So now you're more than ever prepared to now analyze radiation problems. We want to talk about a new parameter called the view factor. It's also called the configuration factor or the shape factor or the angle factor. You may have already guessed that it's probably a factor that has to do with some sort of geometry or the orientation of surfaces, which you are right. So now I'm going to back up a little bit. Imagine a point source looking like the picture here, and you have different surfaces around this point source. We have seen before that if you have radiation going to all the different directions from this point source, a lot of it will be absorbed by surface 3, for example. None of it will be absorbed by surface 2, and some of it will be absorbed by surface 1. We have done an example on this before as well, and I do encourage you, if you haven't looked at the previous lecture examples, go take a look at the example where we are looking at different orientations of surfaces towards an emitting surface. So we already know from that example and the previous conceptual analyses that some of the radiation that between surfaces depends on orientation. It also depends on the properties of the surface, and it also depends on the surface temperature. But for now, we want to define a factor called the view factor just based on the orientation of two surfaces relative to one another. We'll deal with the properties and temperature later to then figure out exactly what is the amount of radiation or net radiation between two surfaces. We'll deal with that later, but the very first factor that we want to define in order to take care of the orientation is the view factor. So for example, in order to use what we call the view factor, we're going to assume that all the surfaces are diffuse emitters and diffuse reflectors, and we're going to call this view factor diffuse view factor. For simplicity in this course, I'm going to call the diffuse view factor just simply view factor. There is a view factor that's called specular view factor, which is the case where you have specular reflection. But in those cases, those could become a little bit more complicated. We don't discuss them in this course. So from now on, when I say view factor, what I mean is diffuse view factor. That is radiation in all the emission and reflection in all the different direction is going to be uniform. So how do we define view factor? First, we'll start with a symbol. The symbol looks like F with subscripts I and J. Take a look at the picture here. You do see two surfaces. One is surface I with area or AI, temperature ITI, and then the normal to the surface is NI, and it's a very small part of the surface. The differential area would be DAI. And the same goes with area J. All those parameters are defined with subscript J. When we want to talk about the view factor, we define it as the fraction of the radiation leaving surface I that is intercepted by surface J. So take a look at surface I. It will be emitting radiation in all the different directions. Some of that will be intercepted by surface J, and the rest of it will be intercepted by other surfaces surrounding surface I. J is not the only surface that's surrounding surface I. There's other surfaces as well. So part of that, or a fraction of radiation emitted from surface I, is going to be intercepted by surface J. That fraction, if it's 30%, 20%, whatever that is, that fraction, we call it Fij. It's very important for you to be careful to have Fij or Ji. These two are two different things. Fij is the fraction of radiation from I to J divided by the total radiation that's going off of surface I. So for example, what goes off of surface I is what's emitted from it and what's reflected from it. So that's why we, in the denominator, what goes off, the total radiation that goes off of surface I is going to be area of I multiplied by the radiosity. Radiosity, the units for that was watts per square meters. It's a flux. So we have to multiply that by an area of the surface in order to actually get the total radiation in the form of power. So AI, JI is the denominator of your relation. That's the total radiosity, or the total power that goes off of surface I, and then in the numerator, the part that is intercepted in area J is basically used. So we're basically saying Qi to J, that is the part of radiation from I that actually is intercepted by J. This ratio, we're going to call it Fij. If you were to write the same ratio for Fji, it would be a little bit different. Be careful with how the I and J are written. When you say Ij, that means from I to J. Now, the exchange between areas AI and AJ, as I said, they're actually different. If IJ or JI are different, and the relationships for them are given to you here. We can derive, based on the knowledge that we have from the previous chapter, we can derive these two relations. But because this may be very time consuming and you may not be very interested at this point to see the derivation, I've put it in the appendix in case you're interested to see what the derivation looks like. Go in the appendix of this lecture note and take a look to see how we actually derive these. It has to do with all those radiation intensities and all those relations that we actually derived and looked at in the previous lecture. So what you know will help to derive these relations. But for now, we just want to do radiation analysis, and that's why we want to see how we should use these relations, not how we derive them.